The next thing I want to look at, we're still considering biological objects in external fields. And the one topic here that's very much related for things like cell separation and dielectrics in the presence of electric fields is a dielectrophoresis force. Now the dielectrophoresis force is present when we have an electric field gradient. Okay, so this would be P dot grad operating on the electric field here, which would give us a force. So if there's no gradient in the electric field, then we're not going to have any force here. So this multiplies, that's a dot product, and that multiplies the electric field here. The direction of the force points away from the electric field gradient or towards, depending on the relative permittivity of the dielectric particles with respect to the medium. And this can be because the different cells have different dielectric constants and different sizes. They will experience a different dielectrophoresis force. And this can be used to separate different types of cells. For example, if you wanted to separate cancer cells from normal cells, they would, if you had a vessel that was conducting both types of cells, they would experience a different dielectrophoresis force, and you could use this to separate the cells. As well, the dielectrophoresis force not only is present for static electric fields, but also AC electric fields. You might think that the time average force in an AC field will be 0, and that's not the case for a dielectric. There will in fact be a force, and it really depends on the relative permittivity of the medium as well as the conductivity. These are the complex conductivities, which in this notation, these include the electrical conductivities as well as the permittivities of the particle as well as the medium here. And this is the analytical formula for a single sphere in the presence of an electric field gradient. Now, I want to look at a couple problems. First, the DC dielectrophoresis force acting on a dielectric particle here. I'll close the previous model and not save the changes. Let's open. This is dielectrophoresis, and look at the model, the geometry file. It has axial symmetry. This is just an electrostatics problem, and what I've done is I've put a single needle above a dielectric sphere here. We can zoom in on this. We have a finer mesh density where we're interested in getting a more accurate solution. So this is the dielectric. It has a particle. This could be a Me cell, for example, with electric permittivity of 10. This is the water region. Okay, and this is the needle. It's an electrically charged needle. In order to simulate an object with uniform electric charge, this is a slightly different type of boundary condition. I choose a floating conductor with equal voltage, and I fix a point charge to one end of it. It doesn't matter where I put the point charge on this boundary. This condition will distribute the charge evenly across the needle here. Now, at the edge of the solution region, I've given a 0 potential. I don't care what happens at the edges. I've moved them out hopefully far enough. And notice I don't need to assign any boundary condition ever directly to the z-axis except here where I have a charged needle here. Okay. Now let's go ahead and solve the problem. It's already been solved, but I'm in the habit of resolving it. Okay. So the needle is above the dielectric sphere. These are the equipotentials due to the needle. And what I want to calculate is the force that's acting on the sphere. And to do that, I will surround it by a contour. I've gone to my contour tool, and I can simply come around here. Okay. And then I can look at the integral values. Okay, and this region is highlighted here, so I'm looking at volume integral. And the force acting on the particle is roughly a femtonewton, 5 femtonewtons, and that is in the that's the z component of the force, so that's pointing along the right. Okay, so this is pointing away from the needle here, so that the particle is repelled from the needle in this case. What I'd like to do is interchange the roles of the particle and the medium and compare the force in that case. So I'm going to go back to the model file. Now, this is my water region, and what I'm going to do, I'm just going to switch the labels. So now the water is the dielectric region, and now previously the dielectric sphere is now water. Okay. Now, what we have, we still have the needle that's charged, and so this would be like a drop of water in a lipid region. Let's go ahead and resolve the problem, save the changes, resolve it. Okay, once again we have a similar looking field plot, and I'm going to surround this with a contour. Okay, we're going to look at integral values. We have the integral value tool here, and the mechanical force, okay, which is now in the opposite direction. This is a little bit greater here, -6 times 10 to the -14 newtons, and it's pointing now to the left. It's pointing towards the needle. So the direction of the dielectrophoresis force depends on the relative permittivity of the particle and the medium here. Okay. Now, I want to illustrate one more problem, and that is the AC dielectrophoresis force. Okay, now this is the geometry. This one, once again, is a AC conduction problem, and it has XY symmetry. What I have are two electrodes. These are pin type of electrodes. These are cylindrical electrodes that are coming out of the solution region here, and I have a dielectric particle, but this would be more like a cylindrical dielectric region as well. For example, an axon or something with cylindrical symmetry, or a cylindrical type of micelle. This is a water region, and I've given it a millisiemens conductivity. The particle has a conductivity of 1 and a dielectric constant of 10. Okay. Now, the edge labels, this is the boundary of the solution region, and I've given that 0 potential, and I don't care what's occurring at the boundary, and really you'd like to push this as far away as convenient. The left electrode has a constant potential of -1 volt. Notice it's not really necessary to mesh the interior region of this electrode because it's at equipotential all the way around, so it's going to be at -1 volt. In the central region, we don't care about what's going on inside of the electrode here. This electrode has 1 volt. Okay. Notice that the dielectric particle is closer to the left electrode, and I'm going to go ahead and solve this problem again. Okay, this is the equipotential plots, and we'll get close to the dielectric particle here. Okay, this shows the relative field strength and the equipotential lines. And I'll go ahead and look at the force acting on the particle. I'll make a contour around. Okay, I need to go to my my tool here, and once again look at mechanical force. Okay, now the mechanical force here is roughly a piconewton, and that would be to the right, because this is a positive value and we're taking the right as positive here. Okay, there is a tiny wide component here because perhaps we're not exactly centered along the bottom boundary here. And what I want to do is, so this is an AC, the time average AC force is non-zero. That's really the important part here. And this has applicability to dielectric spectroscopy or whatever you're putting electrodes inside of a solution. Even though it's an AC current, you will pick up particles that are contaminating your electrode because of this effect. Now, I want to come back to the model here. And I'm just going to move the particle over to the other side. I can just select it and drag it over here, and we can see what the force is over here. Okay, now I can delete my mesh, start from fresh, and I'll just simply remesh the problem. So I wanted to illustrate that the feature how you can simply drag the boundaries around when you're constructing your model. Let's resolve it. Okay. And I'll zoom in. Okay. And we can see the force that's acting on the particle here. I simply create my contour around. I need my integral tool here. And mechanical force. Notice there's many integral values that we can calculate. Okay. Now this time the force here is to the right, so this would be attracted to this particular electrode here. Okay. So I want to conclude. We still have a few more points to talk about,